In the previous lecture, we have started to deal with a very important problem of waves and oscillation and this is regarding the coupled oscillations. Actually, we have seen a very brief introduction regarding these coupled oscillations. You have seen that in case of coupled oscillations, we cannot neglect the feedback energy of coupled systems in from the driven system to the driver. And I have also cited three very important examples of the coupled systems which has actually 2 degrees of freedom. When you say that a coupled system has 2 degrees of freedom, when two objects are coupled, then degree of freedom is 2. It means we need 2 variables in terms of which the motion can be completely specified. Okay. So the first example which we have taken in the introduction for discussing the coupled oscillations, that was actually the 2 coupled simple pendulums. So the first problem or first theory we are going to see is regarding the 2 coupled pendulums. As you can see in this figure that I have shown in this figure number A, there are 2 identical simple pendulums. Each have the bobs of mass m and length L. Since length and mass of the bob are same, so we say that these 2 simple pendulums are identical simple pendulums. Okay. And you can also see that the 2 bobs of these 2 pendulums are connected by a massless spring and ideal spring having a spring constant K, as you can see in this figure. Actually, in first figure A, I have shown that the 2 pendulums are in equilibrium, and in this condition the coupling spring by which the 2 bobs are connected is neither extended nor compressed. So no tension is developed in this spring and the 2 bobs are in equilibrium. Okay. So you can say in equilibrium condition the spring is in its natural length. Okay. Actually the separation between the 2 bobs is such that the spring is relaxed and the system is in equilibrium. But see the second figure where you can see I have shown that the 2 pendulums are displaced from their equilibrium positions. And I have shown in this figure that the bob A has been displaced by psi A from its equilibrium position. This psi A is the displacement of the pendulum A from its equilibrium position. And at the same time, the second pendulum B has been displaced by psi B from its equilibrium position. And in general, we have to take that this psi A is not equal to psi B. Although in the last of this lecture we will see what will happen when psi A is equal to psi B. But to develop a theory, first of all we are going to assume that the displacement of the 2 pendulums are not equal, but those are different. So when the 2 pendulums are displaced or disturbed from its equilibrium position and released, what will happen? Actually, when the pendulum will released from the displaced position, you can see that the 2 pendulums will oscillate about their equilibrium position. Okay. So actually in this lecture we are going to see 2 problems. In this first part of the lecture we will simply discuss how to derive the equation of motion and what informations we get from the equation of motion of this system. And in the second part of this lecture, which we will see in the next lecture, you will see the concept of normal coordinates and normal modes. Okay, but in this very lecture we will only see the equation of motion and how that equation of motion can be solved, what we will have to do for that. All these things we will see in this first part of the lecture. So now let us try to first of all find the equation of motion of this system. As you can see, I have assumed that at any time t, this psi a is the displacement of pendulum A and psi b is the displacement of pendulum B. Okay. So if we assume that psi b is greater than psi a, psi b is greater than psi a, then you can see that the spring will be stretched. Okay. But if psi b is less than psi a, then the spring will be compressed. Okay, because displacement of both of the bobs are in same direction. Okay, in rightward direction, and so if psi b will be greater than psi a, the spring will get stretched. But if psi a is greater than psi b, then the spring will get compressed. Okay, and both may happen, but here we are considering that psi b is greater than psi a. Okay. Now you know, as the two bobs are displaced by psi a and psi b, so the stretching, or you can say elongation or compression of the spring will be what? That will be simply psi b minus psi a. This is the elongation or compression of the spring. And you know, when you multiply this elongation or compression by the spring constant K, then you get the spring force. So the tension developed in the spring or the spring force will be given by K times psi b minus psi a. This is the spring force, or you can say the tension developed in the spring. Okay. Now you can see the figure. When actually this psi b will be greater than psi a and the spring is elongated, then this bob will be actually pulled down by the spring towards its equilibrium position. So you can say when psi b is greater than psi a, then the acceleration of this bob, that is psi b double dot, which means d2 psi b by dt square. This is acceleration of the bob B. Actually, this acceleration will be opposed by the displacement. Okay. On the other hand, in this very condition, the displacement of bob A will be supported by the spring force, and so this psi a dot will be in the direction of its displacement. So what you are seeing here, psi a dot double dot, this will be actually in the direction of the displacement psi a, while in this condition psi b double dot, which is actually the acceleration of bob B, that will be opposed, or that will oppose the displacement psi b. Okay, is it okay? So keeping this fact into our mind, now we can write the equation of motion. And for writing the equation of motion of the two pendulums, let us see this free body diagram. Actually here I have shown this free body diagram for the pendulum A. You know, as mass of the bob is m, so force of gravity mg will act on this bob in vertically downward direction. Okay, and I have shown that this pendulum has been displaced from its equilibrium position by a very small angular displacement theta. Theta is the angular displacement of the bob, and it is very small because we are considering the case of a small oscillation. Okay. The another force acting on this bob will be tension of this spring T. Okay. And the third force acting on this bob is the spring force. Okay. And as I have told you that the spring force acting on bob A will be in the direction of its displacement. And as the displacement of A is from left to right, as I have marked here, so this spring force which is actually K times psi B minus psi A, this acts along the direction of psi A. Okay. Now for writing the equation of motion of this bob A, let us resolve this force of gravity mg into its two components. You can see, since this angle made by the string of the spring with the vertical is theta, so this angle here made by this mg with the string will be also theta, and so this component will be mg cos theta. And the another component which acts just like a restoring force, that will be mg sin theta acting towards the equilibrium position. Okay. So here this mg sin theta tends to decrease the displacement, while this k times psi b minus psi a tends to increase the displacement. Okay. So the net force acting on this bob towards the in the direction of acceleration, what will be that? Here actually this tension T developed in the string is cancelled by mg cos theta. This mg cos theta is cancelled by this T, and the resultant force acting on this bob in the direction of its acceleration will be what? That will be k into psi b minus psi a minus mg sin theta. So if AA is the acceleration of the bob, then according to Newton's second law of motion, you can write the equation of motion. You know, the net force acting on this bob in the direction of its displacement is what? This is minus mg sin theta plus k times psi b minus psi a. And that resultant force will be equal to mass into acceleration. M is the mass and AA I have assumed is acceleration. Now since psi a is the displacement of the bob at any moment t, so d2 psi a by dt square, this will be its acceleration, and this is in dot symbol written as psi a double dot. So I have written psi a double dot instead of AA. So m times psi a double dot, this will be equal to what? This is minus mg sin theta plus k into psi b minus psi. But as you know, this theta is a very small angle. Okay. So this sin theta will be simply equal to theta, and theta is equal to L over R. Here L, that is arc length, will be simply equal to psi a, and R, that will be equal to L. So instead of sin theta, you can write psi a divided by L. So here in this equation you can see I have replaced this sin theta by psi a divided by L. Okay. So the equation of motion of pendulum A is written as m times psi a double dot equal to minus mg over L times psi a plus k times psi b minus psi a. Okay. This is the equation of motion of bob A. Actually, in the similar manner, you can write the equation of motion of the second pendulum. But in this case, as you have seen, that this spring force k into psi b minus psi a opposes the acceleration of the bob. So as the displacement is from left to right, this spring force acts from right to left, that is in the direction of minus in the direction of mg sine theta. Okay, so both mg sine theta plus k times psi b minus psi a opposes the acceleration. Okay, and hence the equation of motion of this bob b will be written as m times psi b double dot equal to minus mg over L into psi b minus k times psi b minus psi a. Okay, here actually sine theta will be equal to psi b divided by L. Psi b divided by L. Actually here this theta will be something different. You can write it theta prime. So because psi b is different from this psi a. So instead of theta, now write theta prime. Okay. Okay. And so this is the equation of motion of the second pendulum B. Now seriously see these two equations, that is equation number 1a and 1b. You should see it. What you are observing? As you know, in case of simple harmonic motion, the acceleration of the particle or the oscillator is directly proportional to its displacement and oppositely directed. But observing these two equations of motion, can you say that situation is like that? Certainly not. Due to the presence of this term k times psi b minus psi a in both of these two equations, it is evident that psi a double dot is not proportional to psi a and psi b double dot is also not proportional to psi b. Okay, I have written it here. You can see psi a double dot is not proportional to minus psi a and psi b double dot is not proportional to minus psi b. But as you know, when acceleration psi dot will be proportional to minus psi, then motion will be simple harmonic. So here we are observing that as psi a double dot, that is acceleration of pendulum A, is not proportional to its displacement, and similarly the acceleration of the second pendulum B is also not proportional to its displacement psi b. So in general we can say that motion of these two pendulums are not simple harmonic. Actually you can see that the acceleration of pendulum A, that is psi a double dot, does not depend only on psi a, but it also depends on psi b, as here psi b is present. So you can say that acceleration of pendulum A depends on the displacement of the another pendulum also, and similarly the acceleration of pendulum B depends also on the displacement of the first pendulum A, that is psi a. So certainly we can say that the motion of the two pendulums in general are not simple harmonic motion. Okay, but let us see what will happen if we consider that the two pendulums are uncoupled. They are not coupled, as the coupling agent is here a spring. So if we imagine that there is no coupling between the two pendulums, when there is no coupling, it means a spring is absent, and if a spring is absent, there will be no spring force, and you can take k equal to 0. So if the bobs are not coupled, in that condition, if your aim is to write down the equations of motion of the two pendulums, you have to take k equal to 0. So taking k equal to 0, what will now the equation number 1a and 1b? You can simply see that this second term, that is k times psi b minus psi a, present in both of these equations will vanish, and so the equation of motion A and B will simply become what? This will be m times psi A double dot equal to minus mg over L times psi A. And this m and this m will cancel out, and your equation will be psi A double dot equal to g over L times psi A equal to 0. And similarly, you can also see that the second equation of motion will be psi B double dot plus g over L times psi B equal to 0. Now see these two equations. These are simply the equations of motion of simple harmonic motion. These two equations represent the simple harmonic motion, because you know the standard equation of SHM is what? This is d2 psi by dt square plus omega square psi equal to 0. This is the standard differential equation of simple harmonic motion. And this d2 psi by dt square can be written as psi double dot plus omega square psi equal to 0. So comparing these two equations with this standard equation of SHM, we can easily say that in this condition the two pendulums execute simple harmonic motion. And what is the angular frequency? At the place of angular frequency omega square, in these two equations you find the term is g by L. So if you consider that omega naught is the angular frequency of the oscillation of these two pendulums, that omega naught will be simply equal to a square root of g by L. Okay. So actually these are the angular frequency when the two pendulums are uncoupled. Okay. Actually in this condition the two pendulums are not correlated with one another, both are independent from one another, and both oscillate freely with this angular frequency, which is actually the standard result which we have learnt earlier. Okay. Now if you want to write down the equation of motion of these two pendulums in terms of this frequency omega naught, you can easily write it. Okay. So let us try to write down the equation of motion which I have defined in equation number A and number B of equation 1 in terms of psi naught, omega naught. You can see that instead of this g by L present in both of these equations, you can write omega naught square. So g by, at the place of g by L in equation 1a and 1b, we will now write omega naught square in the light of this equation 3. And so equation 1a and 1b will become what? This will be m times psi A double dot equal to m g over L, but instead of g over L we will now write omega naught square times psi A plus k times psi B minus psi A. Okay. Now let us divide by this m in LHS to the RHS of this equation, and so this equation simply becomes psi A double dot equal to minus omega naught square psi A plus k over m psi B minus psi A. So this is the equation of motion of the first pendulum A in terms of this frequency omega naught. Actually in the similar manner you can write down the equation of motion of pendulum B in terms of omega naught square, and that will be what? That will be psi B dot equal to minus omega naught square times psi B minus k over m times psi B minus psi A. Okay. Now see these two equations of motion seriously, and if your aim is to solve these two equations, then in order to find out the effect of coupling on each pendulum, these equations must be solved for psi A and psi B. Okay, psi and psi. But instead of solving these equations directly, we shall choose two new coordinates, because when you will choose two new coordinates, the solution will become very easy, very convenient. So actually our aim is to solve these two equations of motion, but not directly. Actually direct solution of these two equations will be not very easy, not very convenient. For convenience, let us introduce two coordinates which we are designating here by x and y, that is capital X and capital Y. And these two coordinates are defined like this. Actually x is defined by psi b plus psi a, and we define y by psi b minus psi a. We have arbitrarily chosen these two coordinates, and now we will try to write down these two equations of motion in terms of these new coordinates x and y. Now you can see, as x is equal to psi b plus psi a, so what will be x double dot? That will be simply psi b double dot plus psi a double dot. Okay, but see the equation number 4. Here psi a double dot is defined, and here you can see psi b double dot is defined. So let us substitute the values of psi a double dot and psi b double dot from equation 4 here. Okay, you can see, when you will add this minus omega naught square psi a and minus omega naught square psi b, these two will be added, and you can take minus omega naught square as a common factor, and the remaining terms will be psi b plus psi a. Okay, and apart from that, there is minus k over m psi b minus psi a plus k over m psi b minus psi a. So I have written it here, and you can see now this term and this term will cancel out, and psi b plus psi a, we have assumed this is x. So x double dot, this will be equal to minus omega naught square times x. Now instead of this omega naught, we are writing here omega 1. Why we write omega 1? You will see its reason sometimes later. Okay, so the first equation of motion in terms of the coordinate capital X becomes x double dot equal to minus omega naught square times x, and you can see this is nothing, this is simply the equation of motion of simple harmonic motion. This is x double dot plus omega square x equal to 0. This is equation of motion in terms of x. Okay, now let us try to find the second equation of motion. As y is equal to yb minus ya, so y double dot, this will be yb double dot minus ya double dot. Again we will substitute the value of yb double dot and ya double dot from this equation 4. Okay, when you will substitute the value, again you will take minus omega naught square as a common factor, then the remaining terms will be psi b minus psi a, and minus k by m times psi b minus psi a and minus k by m psi b minus psi a. These two will be added, and this will become minus 2k over m psi b minus psi a. Okay, now psi b minus psi a, you have seen, we have assumed it as y. So this psi b minus psi a is replaced by y. So y double dot, this is minus omega naught square y minus 2k by m into y. Again you can take this y as a common factor, and so y double dot is equal to minus omega naught square plus 2k by m into y, and this can be written as minus omega 2 square y. Here we should write minus. Okay, see here. This is minus omega 2 square y. Again you can see that this is equation of SHM having angular frequency omega 2. And what is omega 2? Omega 2 will be equal to a square root of omega naught square plus 2k by m. So omega 1 has been written instead of omega naught, and omega 2 is equal to a square root of omega naught square plus 2k by m. And you can see from here that this omega 2 is actually greater than this omega naught, or you can say that omega 2 is greater than omega 1. Okay. And as I have told you that these two equations, that is equation number 5a and 5b, both are the well-known equation of simple harmonic motion. Okay. So as you have seen that in terms of the actual displacement of the bob psi a and psi b, the equation of motion obtained do not represent that the motion is simple harmonic. But when we select two coordinates defined through these two equations, capital X and capital Y, then in terms of these two coordinates, we can easily say that our system is performing or executing simple harmonic motion. Because in terms of the coordinate X and Y, we get the equation of motion of simple harmonic motion. Okay. So I have written it here, you can see, thus it is evident that motion of the coupled system can be described in terms of two coordinates X and Y, each of which has an equation which describes simple harmonic motion. Okay. These two motions are completely uncoupled, because you can see now in equation 5a, you can say that this x double dot is proportional to minus x and it is independent of y. And in equation number 5b, you can see y double dot is proportional to minus y and it is independent of x. So the motion represented by equation 5a and 5b are completely independent from one another, and so these two equations are called uncoupled equations. Okay, these are uncoupled equations and independent from one another. Although the moving parts of the system are not independent from one another, motion of bob A is affected by motion of bob B, but the equation of motion which we have obtained for the in terms of the two coordinates x and y, those equations are uncoupled and independent from one another. So this is a very important and very marvelous fact. Okay, very marvelous fact, and it gives a very tasty recipe for the discussion of the coupled pendulum. Okay. Actually, we will see in the second part of my lecture on this subject that these two coordinates which we have defined here and designated by the symbol x and y, these are actually called normal coordinates. But the complete idea, complete concept of these normal coordinates we will see in the second part of the my lecture. Okay. Now let us see two very important situations. In first situation, we will now see that if we consider y is equal to 0, as you know, y is equal to psi b minus psi a, and you are taking y equal to 0, it means you are taking psi b minus psi a equal to 0. That is, psi b is equal to psi a for all time t. At all time, this y remains 0. We consider it. So if psi b and psi a are same, that is, the displacement of both pendulums are equal and in same direction, then what will happen? You can see, then this y double dot will simply become 0, and there will be only one equation of motion, and that will be x double dot equal to minus omega 1 square times x. Okay, so in this condition, the motion equation of motion will be completely described by this equation 5a, and what will be the angular frequency? That will be simply equal to omega 1, which is equal to omega naught, and you have seen that this omega 1 is equal to a square root of g by l. Okay, as you can see in this figure, actually I have shown that bob A is displaced by psi A, bob B is displaced by psi B, but both psi B and psi A are equal, and both are displaced in same direction. Okay, so in this condition, the effect of a spring is absent, because if psi A is equal to psi B, then this spring will be neither elongated nor compressed. So it will always remain relaxed, always in its natural length. And so there will be no effect of coupling. Both pendulum will just behave as independent of one another. Okay? Actually, in this condition, we simply say that the pendulums are always in phase. These pendulums are always in phase, and the spring is at its natural length throughout the motion. Okay? So when the displacement of both pendulums are equal, then both pendulums will behave just as a simple pendulum, oscillating with frequency omega 1 equal to root over GL. Okay, there is no effect of coupling. But now let us consider the just opposite situation. In first situation, we have considered that y is equal to 0, but now we are going to see what will happen if we consider x equal to 0. When you take x equal to 0, and you have seen that x is psi b plus psi a, so psi b plus psi a is 0. And if psi b plus psi a is 0, it means you are considering psi b is equal to minus psi a. What actually this minus sign refers here? Actually, this minus sign refers that that the displacement of both of the pendulums will be in just opposite direction. As you can see in this figure number D, this pendulum A has been displaced from its equilibrium position in leftward direction, and pendulum B is displaced in rightward direction. So this if we consider that displacement of B is positive, then you have to take displacement of A negative, and in this case psi B is equal to minus psi A. Okay, or if we consider that this A is displaced in rightward direction and B is displaced in leftward direction, actually in this condition a spring will be compressed. A spring will be compressed in this figure number 2, and in first condition the spring is elongated. Okay, but here also this in magnitude both displacement are same. Okay, psi b and psi are same, but directions are different. So you cannot say that the displacement of the two bobs are equal. Okay, actually in this condition you can see, since x is 0, so there will be no meaning of equation number 5a. The only one equation of motion will remain, and that will be equation defined in 5b, which is y double dot equal to minus omega 2 square into y. Okay, and so the angular frequency in this condition of oscillation is this omega naught square plus 2k by m's square root. Okay, so this is the angular frequency in this case, you can see. And as I have told you earlier that this omega 2 is greater than omega naught or omega 1. Okay. So in this very condition, the two pendulums oscillate simple harmonically with the same frequency omega 2, and they are always out of phase, not in phase but out of phase. In first situation, when psi A was equal to psi B, both pendulums were in phase. But when psi A is equal to minus psi B, then we say that the two pendulums are out of phase. It means the phase difference between them is of 180 degree. And as you can see in first figure here, the spring is elongated, and in this second figure it is compressed. So you can say that a spring is either extended or compressed during the motion, and the coupling is effective. So in this second situation, when the first normal coordinate x is 0, in that very condition the coupling is effective. A spring is doing its work. But in first situation, when we have considered y equal to 0, in that condition the spring, the coupling was not effective. The both pendulums were completely uncoupled. They were oscillating, in fact, independently from one another. Okay. So this is all about the equation of motion of the two coupled pendulums. And as I have told you earlier that this lecture is not completed here, because the concept of normal coordinates and normal modes have been not discussed. But the vital problem of this coupled pendulum is the discussion on normal coordinates and normal modes, which we will see in our next lecture on the same problem. Okay. So definitely after watching this video, you must watch my forthcoming lecture on this coupled pendulum, in which we will discuss the concept of normal coordinates and normal modes. Okay. Thank you very much.